Hi everyone, welcome to my channel. And today we will be going to discuss lead code problem, how we can construct a binary search tree from pre-order traversal, right? So we have to construct one BST and we have given one pre-order traversal array, right? How we are gonna do that? Let's discuss and deep dive into this solution. I'm gonna do the dry run and plus time complexity, and as usual I'm gonna write the code for it, right? So I'm gonna discuss all possible way, brute force, mid optimal and the most optimal solution, right? So let's start with some basic concept. What is pre-order traversal, right? So we have given one example, 8 5 1 7 10 and 12, right? So the pre-order is nothing. Pre-order is root, left and right. This is the basically how pre-order is being follow this, right? Pre-order, in order and post order, we already know all those traversals. So pre-order is like root, left and right. And we have to construct the BST. What is BST? What is the properties of BST? Is any root value, the left tree is gonna be smaller than root value, and the right tree will be bigger than root, right? So if I talk about a little bit in term of lower bound and upper bound, which is gonna get used in later in the solution. So if I take 8 here, right, and in this 8, if I say that any value which is coming, and if it is smaller than 8, is will going to come on the left side, and if it is bigger than 8, it will come on the right side. So bigger than, it means is above 8, 8 is my lower limit, and what is my upper limit? Upper limit is max. Anything can come. So any value which is lying in between 8 and the max, at most max, that is basically my for the right tree we can write what is my lower bound will be 8, and what is my upper bound, it will be my int max, right? And if I say for the left tree, what will be my upper and lower bound? So what any value which is less than 8, right, and any value which is less than 8, and what is the minimum value it can reach? So it can reach to int min, and the max value it can go to 8. So this is my BST tree, right? This is my upper bound and lower bound. So that is what I'm trying to just give a little bit a prerequisite before coming to the solution, right? Now let's look into some solution. First I'll discuss the brute force, and so basically I'm gonna discuss 3 approaches. So let's see what is a brute force approach here. The simplest approach, any value which is coming. So let's say this tree doesn't exist and we have first to insert the 8, nothing is there, we create root, we add it, and that becomes our root for the BST. Now the next value comes 5, we check, okay, 8, 5 is less, we go and add it on the left side. Next value comes 1, we go and check, okay, left side it's smaller than 8, we go on next left. Now on the 5, it's less than 5, we go again, we hit none, we add 1. Now 7 comes, okay, again we start from the top, okay, 7 less than 8, it's less than 8 but greater than 5, go and add on the right side, right? 10 again we start from 8, okay, 10 is greater than 8, we go and add it on the right side, because the right side there is nothing, so add it. 12 again from 8, there is a right one, so we go and check that, okay, it's greater than 10, again we add it on the right side. We just do, if we see how we are adding any new value in this tree, is we start from again from the top. And let's say if it is a skewed tree, what is skewed tree? If every node is in a single line, we take n times to add any node, and we have how many nodes? We have n nodes. So the time complexity for this would be n square. So this is little bit time taking. What is the other approach? Other approach is we can construct a in order, and we can use pre-order given, and we can build tree, right? Now how we can do that? So how we can come up with the in order? In order is nothing, it's a sorted pre-order. So let's see dry run and see how to work out. So we have pre-order given, I'll just write it here, 8 5 1 7 10 12, and we have in order given, which is nothing, which is sorted of this, which is 1 5 7 8 10 and 12, right? We have now in order and pre-order, and as we know what is in order, the definition of in order is left, root and right. Now from pre-order we know the first one is the root. So if I just write it here, the first one is root and then left and then right, correct? So we know the first one is 8, which is our root. Using this we can identify in the in order, this is my root. Now in this root we can make one simple uh, uh, separation in between them. Okay, now this is my left and this is my right, and if you can see, this is nothing, this is BST. The middle value is the anything from the middle to right is greater than, anything on left it is smaller than. So this is following the BST properties, right? So if we build a tree from it, how we can build it? Simply we identify, okay, this is my root, we go and say go and build the tree for this and return me the root node. Go and build the tree, return me the root node, right? Go and build the tree. Now here we know 5 is a tree, 5 is a root. Now here again I identify 5 is my root. It's happening in recursion. So go and build the tree for 1, go and build the tree for 7. So it's a 1, so it will be my leaf node, it will return, now it will return back an 8. So this is how we can build the pre-order in order. So if I quickly write one algo, how it will look like is build tree, we pass both pre and in, and here we pass in start index, we pass in end index, same pre start and pre end, right? And we do the same thing. So this will give me build tree for left, so here we will pass the left thing. So whenever we are passing this in start or end, right, we will make sure that this is my right one, and same thing we do it for left also. So this will be my left. How we will identify left or right? So here let's say pre-order whatever zeroth is, zeroth we can consider whatever my pre-start is. Okay, this is my root. Once we know the root, in order we can identify, okay, using this value, all in order we will have one hash map. Okay, we can map, we can have this map is nothing, it's a in order map. Okay, so all the in order will be mapped with the index of, if I take one example, 1 is mapped with 1, 5 is mapped with 1, 1 is 0, so 0 is indexing, and we have 7 mapped with 2. Like this we have a mapping. So using value we can know what is the IDX for in order. Now we know what is the IDX. Now here we can split it. So let's say this IDX is my root IDX. Okay, so anything from in start till IDX is my left. Okay, so in start will be my same, and my end will be in start plus IDX. Similarly for right tree, my start would be plus IDX plus 1 and I end my 1. Okay, similarly we'll do the pre-start also. So we do the index only. So we know like what is the size of this, so we can identify how many nodes and then do the plus minus here. So this is how you can pass left and right, and then we do self dot root left, and here we do root right, and then we return the root. So this is my algo that I have written here. Okay, so this is how you can this is my algo for this approach. Now if I take this approach, right, what will be my time complexity? Tell me. So here we are doing this in order sorting for pre-order, taking the pre-order array and then sorting it, right? It will take off log of n, right? Now again we are constructing this hash map, which will again take O of n, right? And after, to build the tree, we will take again O of n. So if I see, this is my time complexity. If I take a space complexity, we are taking one hash map, which is O of n, and we are using a recursive stack, which will be O of n. So this is my time complexity and space complexity. Now so again, this is like log of n is extra, how we can have more optimal approach. So this is the most optimal approach that I'm gonna discuss. So let's look into this approach. Okay, so I'll take this I'll go in one sky draw. Okay, and here I'm gonna explain. So let me just paste it. So this is my one example, and here I'm taken. Okay, let me take one. Okay, let me choose different color. Okay, first is 8. Now I'm let me make little not opacity. I'll make no, this is not good. Okay, I think I have made it little big, so that's why it's happening. Let me just start again. Okay, so let's say 8 is the first one. There is nothing, we add it, we do nothing. Now the second one, right? For the second one we see, okay, second one, if I see what is the upper bound, lower bound for this 8, as I mentioned earlier. So if I go back and quickly show you what I have written here, uh, 8 and int max, int mean and 8, right? This is my right tree and this is my left tree. I'll take only upper bound because lower bound is already there, we don't need lower bounds. So right tree int max and this is 8. So here for the right tree we have max, and for this we have 8. I'm just writing. Now 5 comes. 5, is it less than 8? Yes, it's less than 8. We go and insert it here. Okay, I'll explain why I need this upper bound in some minute. Now 1 is less than 8. Yes. Less than 1, less than 5. Yes, we go and add 1, right? Now 7 comes. I'm here right now. We have to do it in a single iteration only. I'm here, 7 comes. Now tell me, 7 is greater than 1, right? It's a greater than 1. Now I can't add it on the left side. Can I add it on the right side? No. Why not? Because it's greater than 1 but it's less than 5. So we have in the BST, what does it mean? That from a parent node, all the left side should be small, all the right side should be greater than the parent node, right? So from 8 it should be greater than, from 5 it should be greater than on the right side, from the on the right side but less than on the one side, but it cannot cross the 8, correct? So here 1 on the right side, why we can't add it, we can't do it, this we can't do it. The reason is the parent node is smaller. Okay, so we need this upper bound here passed also, so we can do this kind of a checking here. So now here I have one upper bound telling that on this one we have upper bound 1 and we have 1. Now 7, is it 7 is greater than 1? Yes. Is it greater than 5? Yes. So we can't add it here, it should be smaller, then only we can add it. Okay, now here this is my upper bound, is basically what is the max value we can add. Upper from that we can't add it. Now here we can't add it, we return back. Again here we have 7. Now for 5 we have upper bound 8. Is it 8 is first thing we check with 5. Okay, from 5 is it greater than? Yes. Is it less than 7 8? Yes. So it's less than, we can add. Now we take next value 10. We are here right now 10, and here what is the upper bound? If what I have passed upper bound is 5. Now 10, is it greater than 5? Yes, we can't add it. Now we go back, we are here, 10 is greater than 8, we can't add it, we go back again here. Now here the upper bound is max here, right? Is it greater than max? Yes, we can add it, so we'll add here. Now we have 12, I'm here. Now for 10 the upper bound is, tell me what is upper bound, tell me. Upper bound is max. Now 12 is greater than m? Yes, we can add it. Now if I have to go on the left side, it should be less than 10, then I can add it on this side. Okay, so this is how you can build this, right? Now let's write it, this particular code. Okay, so I hope you understood it. Now let me write. So first we will write base case, second we'll write recursion, then we'll return the response. Okay, so I'll create one helper method. Here I'll pass pre-order and I'll pass upper bound, which I have to maintain, right? and let's add these three things at the top only. These three things we are gonna add here. Now here we are gonna return self.helper, will pass pre-order, and what will pass? Will pass the max value. Why we pass the max value? As I mentioned, from the top the upper bound is max. For the left, upper bound is 8. For the right, upper bound is max. For 10, upper bound is max. For the left, upper bound would, so here if I pass here whatever value if I have to add, so let's say 11 is there here. Okay, so for 11 if I have to add, so for the left side the upper bound is 10. So so can I add 10 on the left side? We can't add. But can I add 9? 9 is greater than 8 and it is less than 10. So we can add here. Okay. So for the 10, the upper bound is, for the 10, the right upper bound is max, and for the left upper bound is 10. So it's less than 10, we can add. If it is greater than 10, we can't add. We go to max. Now on the max side, we can add. Okay. So you getting my point, right? For left and right, we send a different max. So for the left, we send the value only. For the right, we send the whatever upper bound coming from the top. Okay. So for example, 8, upper bound is 8 only. Here I passed. From the 5, if I have to go here, what I will be sending? Well, I'll be sending whatever 8 came. So the upper bound would be 8 here. On this side, it will be 5. On this side, it will be whatever upper bound coming from the top. You getting my point, right? Why I'm sending upper bound from the top? Because it should be less than the upper bound, whatever is the top one. Okay. So let's write it. We have written this helper function. Now let's write the first is the base case. So for base case, we have to maintain one index, global index, which we will keep increasing after adding one value. So let's say this is my value. So self.x, when it reaches the pre-order, what does it mean? It means is when all the array is exhausted. All the array is exhausted. When that happens, we'll just return none. Okay. What is one more case? One more case, as you can see here, is when we will return the none, whenever the upper bound and whatever value that we have to add, if the value is greater than upper bound, will return anytime. If you can see the 7 came, 7 is less than 5, greater than 5 but less than 8, so we added. When 10 came, it's greater than upper bound, it's greater than upper bound, we returned. Here again from max it's less than, so we added. So anytime if it's greater than upper bound, we'll just, what we'll do, we'll return none. So here pre-order self.idx, and anytime if it's greater than upper bound, we'll just return null. Okay. Now what we'll do, we'll create a new node, right? So we have written the base case. Now let's create a root new node basically. So this is my new node, and we add a value. Okay. So we added a value. Now we have to once the new node is created, we move to next index. Now here we will, what we will do, we will go and say go and build me left. Here I will say go and build me right. Now what happened here, I added 8, I created 8, I added 8, and I increased the index to the next. So now next is 5. Now I'm saying go and build my 5 or go build my right. Okay. So when I'm saying go and build my left and the 5 is there, what happens is it's less than upper bound. It's okay, it can be added. Now again, I will create a new node. I'll go and I will increase my IDX to one more. I go and say now add the third one, which is 1. And again, it's okay. No, we are not hitting the base case because the upper base is lower than only. So we add it. Now when we come to 7, we hit the base case. Why? Because on the 7, my upper bound, what it is 5 on the right side. Left side we can't go because it is not less than 1, right? It's greater than 1. Greater than 1, we go to the 7. When we go to the 7, what we are passing? We are passing upper bound. So when we are going on the left side, we pass the left value only. So if I write self.helper pre-order, what we will pass? We'll pass the root value only, right? But when we are going to the right side, what we are doing, we are passing, when we are going on the right side, we are passing upper bound, correct? As you can see, when we are going the right side, 5 is there. When we are going left side, we have 1. So we compare with 1 on the left side. When we go on right side, we compare with the 5. Okay, so here we are comparing with 1, it means is the upper bound is 1. Here we are comparing with 5, it means the upper bound is 5. And what is 5? 5 is coming from the top. So here I pass the upper bound which is coming from the top. Here I pass the root value, which is I'm saying anything value should, if it is greater than root value, return. If it is less than, then only add. So this is my case. Now here what I will do, I will return my root. So this is the code. So let's run it. Okay, something indentation issue, something small. So where is the indentation? Okay, somewhere here it is saying. Okay, so we have float infinity, we are passing. Okay, we don't need this, I believe. Helper I'm passing one float. No, we need this. Okay, what is the issue? Unexpected indentation, wait. So okay, things looks fine. Let's see. Okay. Okay, let me write again. Self.header, we pass pre-order, and for UB, right? I'm passing UB. So for UB, I make infinity. Okay, I believe this block string is causing some issue. Okay, it's working. Now here it's saying okay, there is no X, typo issue, fix that. Okay, something solution doesn't have. Okay, here I have created X and I'm using IDX and X, so this is causing problem. Okay, so you see it passed all the case. Let's submit. Cool, it passed all the test cases. So this is about this BHT, how you can construct it using pre-order. I have discussed all 3 possibility. Only thing left is the time complexity for this. So it will be O of n because we are just going one node only once. So that's it. So thank you so much for your time, and please do subscribe and leave a comment and connect with me on LinkedIn if you need help from me one-to-one. Thank you so much. Good day.